Hello everybody, welcome back to the Graph Algorithms course. Today we're going to be talking about notions of connectivity in a graph. In particular, talk about connected components and how to compute the connected components of an undirected graph. So, to begin with, last time we talked about this notion of reachability. What does it mean to be able to reach another vertex from a given one? And what we'd like to understand now is really what sort of classifies reachability in a graph. We really, not just from a single vertex, we sort of want to understand which vertices are reachable from which others. And it turns out that for an undirected graph, there's actually a very clean categorization of this. In particular, for any graph G, we can always partition it into connected components, such that two vertices V and W are reachable from each other, if and only if they're in the same connected component. So sort of we break this graph up into islands, where any two islands are completely unconnected from each other, but within any island you can get from anywhere to anywhere else. So just to make sure we're on the same page, if we have the following graph, how many connected components does it have? Well, this graph is going to have 4. Sort of, if you look at these 4 things, from each of these things, they're all connected up, but there are no edges between any pair of them. Okay, so let's see how the proof of this theorem works. Why can we always divide it into connected components? And basically the idea is you need to show that reachability is an equivalence relation. That means 3 things. Firstly, that V is reachable from V, which is easy. Also, that if V can be reached from W, W can be reached from V, which sort of is just following the path in the opposite direction. And then there's the difficult one, that if V is reachable from U, and V is also reachable from W, then W is reachable from U. What this says, if you sort of take V and you take everything that it connects to, in fact, everything in that whole region connects to everything else in that whole region. And that last step is not so hard once you write it down. The point is that you can reach U from V, which means that there's a path from V to U. You can also find a path from V to W. And if you just sort of glue these paths together at V, then you have a path from U to W. So they can be reached from each other. Okay, so that completes the proof. But what we'd now like to do is do this algorithmically. Given a graph G, we'd like to find the connected components of this graph. Okay, fair enough. Let's find an algorithm. Well, the basic idea of this is pretty simple. If you run explore of V, this finds the connected component of V. It finds everything you can reach from V. That's the whole connected component. And you just need to repeat this to find all the other components. And it turns out you can do this actually with only sort of a slight modification to the original depth-first search algorithm that we saw. Now, in order to make this algorithm we're about to see a little bit more cleanly, we're going to modify our goal a little bit. Instead of actually sort of returning sets of vertices that are our connected components, what we're going to do is we're going to label the connected components. We're going to give everything in the first one a label of 1, and everyone in the second component a label of 2, and so on and so forth. Okay, so how does this work? Firstly, we modify our explore procedure. We visit the vertex. We also make sure to visit all of its neighbors, but we also assign the vertex a number corresponding to its connected component, this CC number. Now, the thing is that this variable CC is not going to change as we make these recursive calls to explore, and so everything else that gets found in sort of the same explore will all get assigned the same number. However, when we actually run our depth-first search, we're going to, between different explorers, between different vertices that we explore and then go off to find a new vertex, we increment this number. And so the second explore that we do, everything gets a number 1 bigger. So to see how this actually works, on this graph, our counter starts at 1. We find an unvisited vertex, say that one, it gets labeled with a 1. We keep exploring from that vertex, and we find these other 3. All of them get labeled with 1. But now we're done exploring that first vertex, so we increment the counter and find a new unexplored vertex. So say that one, which we now label 2. We keep exploring, and the other vertex that we found also gets labeled with a 2. But then we finish that explore call. We now increment our counter to 3 and find a new vertex, this one. We explore that, and everything we find gets labeled with a 3. And now we're done. We've got 3 connected components. Everything in the first one is labeled 1. Everything in the second one is labeled 2. And everything in the third one is labeled 3, which is sort of what we wanted. Okay, to show that this is correct, we note that each new Explorer call finds a full new connected component because it finds everything connected to that V. And of course, because V had not been found yet, it was not in a connected component that we'd already seen. Secondly, because of the way this outer loop in depth first search works, every vertex eventually gets found, because every vertex we eventually check to see if it's been visited, and if not, we explore it. Now, the runtime of this is basically just the runtime of depth first search. We only made sort of cosmetic modifications to it. So the runtime is still O of size of V plus size of V. Okay, so that's our discussion of how to compute connected components. Next time, we're going to talk about some other applications of depth first search. So I'll be happy to see you in the next lecture.